Okay, we're going to start the unit on solutions. Many of the things that we're going to talk about in solutions you've seen before, either when we talked about mixtures or in previous science classes. This unit is heavy in vocabulary, so we're going to have a lot of vocabulary words thrown at you. So you need to be able to keep track of these. Make sure you look at your vocabulary list that I have given you in class. Okay, so we're talking about solutions. So let's review what a solution is. Okay, a solution is a homogeneous mixture of two or more substances in a single phase. Homogeneous means it is uniform throughout. You can't see one from the other. An example of a homogeneous mixture would be vinegar in water or salt water. That would be a homogeneous mixture. Okay. In a solution, it's made up of two things. It's made up of a solvent and it's made up of a solute or multiple solutes. Okay. One substance of your mixture is considered your solvent, the thing you have the most of, and the other is considered your solute. Your solvent plus your solute gives you your solutions. Okay, so let's just define this in a way that is a little bit more precise. Your solute is the part of the solution that is being dissolved. It is the thing that you have less of. So if you have salt water, your solute would be salt because you have less salt in salt water than you have water. So solute, the thing that is being dissolved, the thing you have less of. Your solvent is the part of the solution that dissolves the solute, the thing you have the most of. You can only have one solvent, but you can have multiple solutes. You can dissolve sugar and salt in water. Right? There you have two solutes, one solvent. Okay? Your solute plus your solvent gives you your solution. Okay? Your solution is that homogeneous mixture, and it's made up of a solute or solutes plus a solvent. So the way I remember which is which, solute has less letters than solvent. So solute, there's less of them, less stuff. Solvent is the thing you have the most of. Okay, so let's talk about different typical solutions we see. So if you were to look at an alloy, which is a homogeneous mixture of solids, your solute in that case would be a solid, and your solvent would also be a solvent. So like your 14 karat gold, your solvent is gold. Your solute is any of those impurities. Okay. Another example of a solution is where you have a solute that's a solid and your solvent is a liquid. And that's what we were just talking about, the salt water. Your solute is your salt that you dissolve in your solvent, your liquid. Okay. You can also have a solute that's a gas that gets dissolved in a solid. And this is when you have hydrogen dissolved in palladium. It's used as hydrogen storage, and this is used a lot in the space industry. If you have a liquid solute and a liquid solvent, would be something like an alcoholic beverage. A lot of it is water, and then you've got some alcohol in there. Your alcohol is the liquid, is your solute, and your water is your solvent. Or vinegar that you buy at the store. Vinegar is 5% acetic acid, that is your solute, and 95% water, that is your solvent. You can dissolve oxygen in water. That's another type of solution, gas into a liquid. Or you can have a gas solution, and that's like the air we breathe. Our solvent in the air we breathe is nitrogen because that's what we have the most of in the air. But we also have oxygen, that's our solute. We have carbon dioxide, that's a solute. In Houston, we have a lot of water vapor, the humidity, that's also a solute. Multiple solutes, but your solvent is nitrogen because it's the thing you have the most of. Okay, so what is solvation? Solvation is the process by which you dissolve. It's the process of dissolving, and it's going to depend on the type of compound you have, whether it's ionic or covalent. Okay, but generally what happens is first, your solute particles are surrounded by the solvent particles. So what does that mean? You have salt, you put it in water, And now your water molecules are going to start surrounding your salt, your NaCl. And in doing so, those solute particles, your NaCl, are separated individually and pulled into solution. They're separated because they're surrounded by the solvent. That process is called solvation. Okay? If you have an ionic compound and you put it in water, that's called an aqueous solution because it's dissolved in water. So many reactions involve ionic compounds in water, aqueous solutions, like your double replacement reactions. You need to have your ionic compounds in a solvent in your water for the reactions to occur. And why is it that they occur in water but not when they're solids? Well, when you put, let's say, KMNO4, that is an ionic compound. When you have it by itself as a solid, it's hard for molecules to get in there and react. But when you stick that KMNO4 in water, you're going to have that solvation process where you're going to have the water molecules, that's the red with the 2 white dots. Unfortunately, my animation isn't working. The red with 2 white dots are going to come and they're going to start surrounding this KMNO4. K is the yellow, MNO4 is the blue with the red dots. And those water molecules are going to start surrounding these. And those water molecules are going to kind of get in the middle between these guys and kind of push them apart. And in doing so, now you have K pluses available, you have MNO4s available. You don't have KMNO4 together because they've been dissolved and solvated. Okay? So that is called dissociation. For an ionic compound, when your ionic compound solid gets separated into aqueous ions when it's in solution, that is called dissociation. So if you have sodium chloride solid and you stick it in water, what you're going to end up with when you're looking at it in water is you're not going to see an NaCl anymore in water. What you're going to actually see is an Na plus, which is surrounded by water. That's what that aqueous means. And you will see Cl minus, which are surrounded by water. So these guys right here, these water molecules kind of shove themselves in here and surround each one of these dots individually. And in doing so, pulls them apart. That is called dissociation, and that happens for ionic compounds only. You dissociate into ions. You dissociate into your cations and your anions. Okay? So the process in which this happens is your solute, first step is your solute-solute attraction is broken up. So what does that mean? You have sodium chloride, NaCl. There's an attraction that is holding your sodium and your chlorine together. That's that electrostatic charge that holds them together because it's an ionic compound. Well, that process, that attraction is broken up when the water surrounds it, and you go through this dissociation. That attraction is broken up because water shoves itself in there and is able to separate them. Dissociation, separation of ions from each other in solution. So if you have NaCl plus water, the Na ion becomes hydrated, surrounded by water, and the chlorine ion becomes hydrated, surrounded by water, and they move away from the crystal into solution. Remember, your ionic compounds are in a crystal lattice. You put them in water, they start moving away from this crystal solution, they get dissolved. Each ion in the solution acts as though it was present alone. When they are dissociated, now no longer do you see the sodium with the chlorine together. Now you see sodium by itself and chloride ion by itself. You don't see them together. They're uniformly mixed. That's dissociation. Okay? The solvent-solvent attraction is broken up. That means the water is now no longer more attracted to itself. It's attracted to the other things there. And then you have this solute-solvent attraction forming. And that is solvation. That's surrounding the solute particles by your solvent particles. So that is true for ionic compounds. Dissociation. For covalent compounds, you don't have dissociation because covalent compounds are not made up of ions. Your covalent compounds or your molecular compounds, what you get is something called dispersion. So again, because it is solvation, your water molecules do surround your molecular compounds or covalent compounds, but they don't break them apart. So if you put in like some organic compounds into water and it dissolves, each one of those organic compounds gets surrounded by a water. So if you have an organic compound here, it's going to be surrounded by a bunch of these waters all around it. Okay? That is called dispersion. Your molecules stay intact, but they're still solvated. They're still surrounded by water molecules, but they're not broken up into parts. Okay? When you're talking about solvation, we always like to say like dissolves like. And when we talk about like dissolves like, we're usually talking about polarity. If things are very, very polar, they're going to dissolve in things that are polar. If things are nonpolar, they're going to dissolve in things that are nonpolar. So for instance, if you look at oil and vinegar, everyone knows that those separate. Why do they separate? Why do you have to shake your salad dressing? Because you want to mix them together, because otherwise they naturally separate. The reason they naturally separate is that vinegar is very, very polar. Your olive oil is very, very non-polar. So they don't like each other. Like dissolves like. They're not similar enough to each other for them to want to dissolve. But if you were to put vinegar and water, those are both polar. So those mix well together. You make a immiscible solution because they mix well together. Okay. So that's one thing you want to remember about solvation. We always like to say like dissolves like. One of the reasons that soap is such a good cleanser for washing dishes is because soap is a very, very long molecule. And because it's such a long molecule, what one side of the molecule is doing, the other side doesn't know about because they're so far apart. So your soap molecules have a side that is polar and they have a side that is nonpolar. So if it needs to clean something that is greasy, that has oils in it, those tend to be nonpolar. The part of the soap that's going to clean that is going to be the nonpolar part. It's going to dissolve it and be able to wash it away. If you're trying to clean something that is polar, something like a vinegar out of something, or a wine, or something like that, you're going to use the part of the soap that is polar. Okay, so how do we know that we have ions present in an aqueous solution? Beyond the fact that they're ionic. Not all ionic compounds fully dissolve, are fully soluble, and you know that from your solubility tables. So how do we know that we have ions are present in aqueous solutions? Well, we see something called electrolytes. Electrolytes are just basically ions that are present in a solution. Okay, they are things that completely dissociate or nearly dissociate into ions when you put them in water. And because they dissociate into ions, they conduct electricity. Because what is electricity? Just movement of electrons. What are ions? Ions are things where electrons have moved. So if you have something that is a strong electrolyte, something that is dissociated completely or nearly into ions, they're called strong electrolytes. Something like hydrochloric acid, magnesium chloride, sodium chloride. Those are strong electrolytes. You stick them in water, they are going to completely dissolve and they're going to completely dissociate to form an electrolyte. So if they conduct electricity, what does that mean? That means you can light up a light bulb with it. So if you were to have a strong electrolyte like copper chloride, that's another strong electrolyte, and you were to make like a galvanic cell like this, you can, because of the movement, because of the dissociation of a copper and chlorine and those movement of electrons, you can use it to light up a electron. And this is the whole process of electrochemistry. Making batteries uses this sort of thing. Also, electrolytes are those things you're supposed to have when you're dehydrated. And why is that? Electrolytes are things that can permeate through a cell much better, and they bring the water with them. So your Gatorade is going to be full of electrolytes, which means it's full of ionic compounds. Okay, compounds that don't dissolve fully in water, so mostly covalent compounds and a few of your ionic, but mostly covalent compounds that don't dissolve in water but do not conduct electricity, those are called non-electrolytes. Something like sugar, ethanol, ethylene glycol. You stick any of those in water, they might dissolve, but they don't break up into ions. So they don't break up into ions, so you're not going to conduct electricity. You have non-electrolytes. They might be dissolved, but they're not ionized. They're not dissociated fully. Okay, so to review, an electrolyte is a substance that dissolves in water to give a solution that conducts electric current. In other words, it makes ions. A non-electrolyte is a substance that dissolves in water like sugar, to give a solution that does not conduct an electric current. It does not dissociate. It might disperse because it's covalent, or it might just be an ionic compound that doesn't dissolve. So you don't have an ion, that does not fully dissociate. So you don't have enough ions in there for there to be a movement of electrons. So solutions of electrolytes can conduct an electric current. The positive ions and the negative ions dissociate. They separate into a solution, and then those mobile ions can move a charge from one point to another, which is why they conduct electricity. Okay? So those solutions of non-electrolytes cannot conduct electric current. When a non-electrolyte dissolves in water, there's nothing charged. You didn't ionize, you didn't dissociate. So there's no charged particles in solutions. Therefore, there's no pathway for the movement of those electrons to move current. Okay. So if you're an ionic compound and you are a solid, you don't conduct electric current until you stick them in water. Once you stick them in water, your ions then become mobile. When they're solids, they're not mobile. But when you stick them in water, they're mobile, and then you can conduct current. Okay, a few more things we need to talk about. Surface tension. Why do more dense objects sometimes float? How come you can see a paperclip floating on water, or those little bugs that you see that walk on water, or if you're flying, little whatever this is called. I'm not a fisher person. Whatever this is called. Why doesn't it just sink? Why does it just float on top? And the reason for that is surface tension. So if you have, let's say, some molecules, your molecules are that are inside, that are in the bulk, what's called the bulk of your solution, have many places where they can interact. They can interact with all the molecules around them, that they're surrounded by them, as opposed to the ones that are on the surface. The ones on the surface can only interact with the ones that are directly to the right and left of them and below. There's no molecules, no water molecules to interact with above. And when there's nothing to interact with above, the molecules on the surface are mostly attracted to the molecules in the bulk of the solution. So your attraction pulls those surface molecules inward, which minimizes your surface area. And then you end up kind of with a little skin, which resists penetration. Doesn't mean you can't penetrate that surface of the water, but it gives you like a little skin, a little barrier, which then makes things float on top. And that is surface tension. Okay? Viscosity. So viscosity is the resistance of a liquid to flow. When liquids flow, you usually have the top layer of the liquid flowing over the layers below it. And if there's a lot of attraction between the molecules or the compounds within a liquid, they're going to hold on to each other pretty tightly, and they're not going to want to flow. So the viscosity is that resistance of liquid to flow. So like syrup is very viscous. There's a resistance to flow, so it flows much slower than water. Okay, and this viscosity is the result of the intermolecular attractions, the attractions in between molecules. Okay. Okay, last thing we're going to talk about, and it's probably one of the most important, that is solubility. So what is solubility? Solubility is the maximum amount of a solute, the thing you have less of, that will dissolve in a given quantity of solvent at a specific temperature. Okay, so what does that mean? How much salt can I dissolve in 100 milliliters of water at 100 degrees? Okay, because at 100 degrees, I can dissolve a certain amount of salt in 100 mils of water. But if I warm it up, I can put more salt in there. Okay, so the solubility is that maximum amount, the maximum amount of solute that will dissolve at a given quantity of solvent at a specific temperature. You can have an unsaturated solution. An unsaturated solution is when a solvent holds less solute. In other words, you can still dissolve more solute than it can normally at a given temperature. So let's say you have 100 milliliters of water. And your solubility is, for this ionic compound, is you can put in, I don't know, 10 milligrams of your solute in. If you only put 8 milligrams in, you're unsaturated because you can still put in 2 more milligrams of your solute and have it dissolve. So if you're unsaturated, you're holding less than the maximum. If you are saturated, if you're a saturated solution, you're holding as much, exactly as much as your solubility allows. It's when your solvent can hold as much as solute as it normally can at a given temperature. So you're at 100 degrees, you have your 100 mils of water. You can put in 10 milligrams of your ionic compound in there and have it dissolve. How much do you have in there? Exactly 10 milligrams. You are saturated. If you even put one more little drop of your ionic compound, then it will not dissolve. It'll just float to the bottom because you've hit that saturation point. You are saturated. Not a single more compound can be dissolved. Then you have something called supersaturated. That's when a solvent can hold more dissolved solute than it normally can at a temperature. And how is it that you can hold more than what is allowed to be dissolved? Well, you play a little trick. You dissolve a bunch more at a higher temperature. Then you let it cool down. It's now dissolved in water, and you let it cool down to a lower temperature. So you force things to be dissolved at a higher temperature, you let it cool down. So now you are supersaturated. This is an unstable solution, and just about anything will make those things pop out of solution. You'll end up with a precipitate at the bottom. So let's talk about these three things in terms of pictorial. Okay, so an unsaturated solution says, okay, you've got a little solution, you got some water, and you're putting some salt in there. You can put in more solute. More solute dissolves in there. You still have space for more solute. Saturated solution, no more solute dissolves. So here's your solution. You put more in there, and you're going to end up just with that stuff at the bottom. It's not going to dissolve. A supersaturated solution it's unstable. So you're past the saturation point, but you forced more stuff in there. But now you shake it a little bit, and all of a sudden you get these little crystals. Using supersaturated solutions is how they make rock candy. So as you go from an unsaturated to a supersaturated solution, your concentration, the amount of your solute you have in solution, increases. So you need to know these three things in order to understand our next section, which is on solubility curves. Okay, there are a couple of tutorial videos that give you a bit more information on saturation of solutions and how they work, and it's in your best interest to watch them. They're in this PowerPoint for you to watch at home. Normally we do a lab doing these, but we can't do it this year because of COVID. Okay, so what affects how fast the rate of solubility, how fast something dissolves? So the rate of solubility, the speed at which something dissolves, depends on several factors. Number one, the size of the solute crystals. It depends on the surface area. In other words, if you have 5 milligrams of sugar, some of it is granulated, so like kind of crushed up, and you have 5 grams of it that's just in a sugar cube. The thing that has the higher surface area, that's going to be the granulated one, is going to dissolve faster than the cube of sugar. And why is that? Solubility, your solvation, depends on the surface area. If you are, the way the solvation occurs, it goes layer by layer by layer. It's going to dissolve the first layer, then it will dissolve the second layer, then it will dissolve the third layer, and so on and so forth. If you only have one cube, there's not that many layers. It takes a much longer, as opposed to if it's all crushed up, every single one of those little crushed up pieces of sugar have surface area available, so it's going to dissolve faster. Okay. Next thing that affects the solubility of a solute in a solvent is the vigor and duration of stirring. So if you put sugar in water, you're making Kool-Aid or something, you put sugar in water, if you just let it sit there, it's going to dissolve eventually. But if you give it a little stir, it's going to dissolve faster. That's going to affect the solubility. So the vigor and the duration of stirring. The temperature of the solvent will also affect your solubility. If something is hotter Will it dissolve faster or will it dissolve colder? And it's going to depend on what it is. If it is a solid or if it is a liquid, as you increase your temperature, your solubility increases for solids and liquids. So why is that? As you increase your temperature, your kinetic energy increases, so your motion and collisions between the solid and solvent increase. So they're moving around, you're forcing more of those interactions for that solvation, and they're going to dissolve more. And everybody, you've all seen this. You know that sugar dissolves better in hot water than it does in really, really cold water. So if you're like making lemonade, or if you're making a sweet tea, you put the sugar in when it's hot, not when it's cold, because it's going to dissolve faster and you can get more in solution. The opposite is true for gases. For gases, your solubility decreases as temperature increases. As it gets hotter, it's harder to force a gas into its solution. And why is that? For the same reason that it's hard, it makes it easier for solids and gases. You're still increasing your kinetic energy. So if you're increasing your kinetic energy, these gases want to escape into the atmosphere. They're not going to want to stay in solution. They're moving around so much, they're going to escape. Okay. Last one, the pressure. If you increase the pressure on something, if it is a solid or a liquid, there's very little effect. Why is there very little effect? Because those solids and liquids are already pretty closely packed. You can't force those molecules closer together. There's very little effect. But if you increase the pressure on a gas, you're forcing that gas in. It's going to increase your solubility with pressure. It's squeezing that gas solute into solvents. So you need to know these 4 steps. Remember, rate just means how fast something goes. Okay, and just to get a general view of what it looks like, agitation, that's that stirring. If you stir fast, something's going to dissolve fast. This is talking about solids and liquids. If you stir fast, it's going to dissolve fast. If you stir slow or don't stir, it's not going to dissolve fast. It's going to dissolve slow. So temperature for endothermic reactions or for solids and liquids mostly, it's going to dissolve fast if you're hot. It's going to dissolve slow if you're cold. Surface area, that's the size of your sugar granules. It's going to dissolve fast if you have it all crushed up. It'll dissolve slow if you have large chunks. Just like ice melts faster when it's crushed up than when it's a large chunk, same idea here. It's that surface area. Okay, so there is a bunch of slides after this that talk about mixtures and different mixtures, suspensions, things that we've talked about before that you are responsible for, that you must know for your test. But we're not going to review it because you should know it already and we want to spend our time doing the math.